away, please.
So, who did not send the short talks? I heard that there are 3 talks missing. 2. So, you either give a Blackboard talk or you send your PDF now. Stop being on the computer. Just send the PDF. So, okay, very good. So with that out of the way, I'm going to erase this because you'll get 2 emails very shortly. And then off we go. Okay. Let's see. Yes, here it is. Okay. So we were doing, a long time ago, we were doing the sitter space. Okay. And remind you. So if you do coordinates, if you choose coordinates like so, should I keep this closed or? Okay, so if you choose coordinates like this, 1, 2, 3 is just x, y, z here. Then if you plug that over there, then hopefully, if I didn't mess anything up, you should get that they add up to 1 over h squared. Okay. Now one thing, if you notice here, x naught plus x4 equals minus 1 over h eta squared, and if eta is negative, then you see you only cover some fraction of x naught plus x4. There was some question after the lecture about why you only cover part of the manifold. So the sitter space, if you visualize as the hyperboloid, there's a coordinate singularity. So that you only cover the upper half here, okay, with planes. Okay, which is, for us is going to be good enough. So we're going to specify the initial state of the system here on this time slice and then time evolve it from this point on. Let's see, I guess with Chiara, you guys saw Penrose diagrams, is that right? Causal diagrams. Okay, so to see the Penrose diagram, you do the following. There's another way of slicing the sitter space, which is with spheres. So you take, so this you slice it with planes. So the sitter is so symmetric you can slice it in many different ways. You can slice with planes, you can slice with spheres, you can slice with hyperbole. So, but with spheres it's nice because you cover the entire manifold. So you can take your slices, your time slices, to be spheres like this. So these are called global coordinates. You literally parameterize these x1 to x4 by a 3-sphere. Okay, so x1, x2, x3, x4 equals r times. So you exploit the fact that cosh squared minus sinh squared equals 1. So this is like r sinh tau, and these guys add up to r cosh squared tau, and that's how you get the global slicing. So I'm not going to write that up. I'm just going to write down the metric. So this is tau. Tau is the coordinate that allows you to change between the spheres, plus r squared cosh squared tau over r times the omega 3 squared. This is the round metric on the 3 sphere. So here you see that the sphere is has first contracting radius at tau equals 0. It has radius r, and then off it goes, it expands. So if you do a little redefinition of time coordinates like this, cosh tau over r equals the cosine big T over r inverse. So you introduce this coordinate big T, then the metric looks like so: r squared over cosine squared T over r minus dt squared over r squared plus the omega 3 squared. Okay? And so now this big T coordinate will run, also the cosine blows up. So if you think in terms of T over R, so it's conformally equivalent to this manifold. So you have just the standard line, like a linear line element, and you have the line element of the 3 sphere. So, and the point is that this goes from minus pi over 2 to pi over 2, right? So if I plot here T over R, so 0 minus pi over 2, pi over 2. And as usual, the azimuthal angle on a sphere goes from 0 to pi. So this would be, and so the Penrose diagram looks like a square. Let me be color consistent. So the spheres here are like this. So this is a 3 sphere, okay? Every point here is a 2 sphere. So this is, sorry, I used to be much better at this. So this is a 3 sphere, and then here, sorry, I don't make up these names, okay? So even though it's like this is the North Pole, this is the South Pole of the sphere. So they're here, so they shrink to a point. So not all points are equal on the Penrose diagram. So this is North Pole, this is South Pole, and then each of these is a 2 sphere, okay? So then this guy here is a 2 sphere here, okay? Now if you look at those flat slices, they slice the Sitter space like so. They get a bit distorted because of the squashing of the space, and so that's what the Penrose diagram looks like. I mean, importantly, there is a horizon, so that even if you wait forever sitting on the North Pole, you never observe the entire manifold, okay? So if you shoot your light cone backwards, you can see everything that happened here, but everything that is in this region, you never have access to, even if you wait forever. So that's unlike flat space, I remind you. So contrast, in flat space, the Penrose diagram looks like this. So if you wait long enough, then you collect all possible information of what happened, okay? So there is a horizon. Okay. Now, there is a natural set of coordinates for someone that is a geodesic observer here. This I'm sure Geo will tell you all about. So this is kind of the infalling observer, someone that sits at, say, the North Pole of the sphere in the sitter space. So this person can do experiments and collect the results of such experiments within this region of the space-time. And actually, time translation is an isometry. So the space-time, from the point of view of the natural clock for this individual here, is there's some static notion of time here. Okay? So this is called the static patch. Very interesting. I'm not going to say a single word about it in the lectures, because we are really interested in these late time slices that I was drawing with yellow. I realize now I messed up with the color coding. So we are interested here because this is kind of like end of inflation. There is some funny name for observables computed here. They're called meta observables. Because you see, from the point of view, so we're interested in correlations that are deposited over long distances from the point of view of this late time slice. So they're never accessible to an observer that lives inside of this geometry. So you can only measure this if you experience it from the outside. Okay, so we call them meta-observables. So like, what the hell are we talking about if we can't measure them? But the point of inflation is that we are meta-observers of inflation. So our universe doesn't look like this. Our universe looks something more like the following. So we have inflation. But then the Penrose diagram gets a little bit taller, and then we glue onto some other eras, like radiation era, and we keep stretching this. And now we are being dominated by a different value of cosmological constants. So we glue again a Penrose diagram. It's going to look something like this. Okay, it maybe has some shape here, and then it looks something like this, the Penrose diagram. Okay? So inflation. So our universe in a tiny bit of blackboard. So this is inflation. This is like the radiation era, radiation domination, matter domination. And this is cosmological constant, dark energy domination. So, of course, I just made up these curves here. I have no idea what the curve looks like. But the point is, our asymptotic future looks like this. It will look like a little Penrose diagram with different value of h compared to here. So these are just patches of the sitter that are kind of glued together. And why am I drawing you this thing? Well, we sit somewhere here. Again, us from the beginning of the lectures. We are somewhere here. We have some asymptotic future where everything we're ever going to be able to observe looks like this. Okay. So this picture could be, this square could be much bigger, in which case we're only going to access a tiny fraction of inflation. But the point is, right now we measure something a little bit different. We measure stuff within here. But you see now, from the point of view of a static observer, during inflation, there are correlations that are imprinted over long distances that I would not be able to measure But from this point of view, I can totally measure them because they are within my light cone. Okay? So we are meta-observers of this de Sitter phase. But we are infalling observers, we're kind of static observers of this de Sitter phase. So both are important. Yeah. So we're meta-observers here. And here we are static observers. Okay? So both are important. My focus on these lectures will be on the meta-observer, because that's related to inflation. Okay. Questions? Yeah.
As a co-mobile observer.
Yeah.
But in this case, meta observer, I don't think, I don't understand.
Yeah, so we're going to keep track of certain co-moving waves. And we are here, we are co-moving observers. But during this phase of our FRW universe, the universe is very well approximated by pure de Sitter. So if you thought, oh, this is pure de Sitter, then the objects that I'm computing from the point of view, if I forgot about all of that, the objects, so maybe let me say it differently. So if I had only one de Sitter universe, what I'm doing is I'm doing this computation. Then what I'm saying is, aha, it's not de Sitter. Actually, this is not the asymptotic future. It's very late time, but not infinitely late time. And then I continue. And I paste something else here. Now, from a certain point, it looks like de Sitter again. And we are somewhere here. And even though this was not accessible to the co-moving observer here, it's accessible to us co-moving observers up here. Okay? So then this object makes sense for us. Okay?
Sorry. I think it's related here.
Ah, yes.
From the point of view of causality, why do we use Poincaré coordinates in cosmology? In calculations?
Because the point of inflation is to make the universe very uniform and in particular very flat. And Poincaré coordinates for the de Sitter space, they make it obvious that at very late times, the slices in which, so again, this is not pure de Sitter. If you wish you had pure de Sitter here. We're going to take a time slice, and then we're going to delete this part, and we're going to glue to some late time cosmology. But we want this slice to be pretty damn flat. Okay, and that's why we like to use Poincaré slices. I mean, you could wonder, and people did wonder, what happened if you glue the big sphere, or if you glue the piece of a hyperboloid? And yeah, now in any case, this is a bit speculative. I mean, there are now maybe some hints. There are the topology of this slice might be slightly hyperbolic. Anyway, so you could have made different choices, but the standard way of thinking about it is in inflation is that this is very well approximated by a flat slicer. So that's why we use Poincaré coordinates.
Thank you.
Also, because the kinematics is much, much simpler. We're going to talk about Fourier modes here, because the slices are flat. If you were to go to hyperbolic slices or spheres, then you have to talk about angular momenta, and then it's much more complicated. Wigner symbol, blah, 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 blah. So it's much easier to think in terms of momentum space. Any more questions? Okay. So let me, the isometries in the original, the isometries here are very simple. They're just either rotations or boosts, right? Respect to x0 and x3. And they get a bit convoluted from the point of view of Poincaré coordinates. So let me just show you how they act. So the metric looks like so. And so what isometries are simple here? So there are 3 translations. They're just shifts in X. There are 3 rotations. There again, rotations in X, some rotation matrix dot X. Then, well, if you're holographers, then you all know that there's a scaling isometry, right? One dilation isometry where I take eta and X and rescale. So if I do the experiment today or tomorrow in a bigger lab, I get the same results. It's a good way to get funding. Tomorrow I need a bigger lab because of dilation symmetry of de Sitter space. The 3 others, though, are tricky. And they're like really the analog of de Sitter boosts. And we call them special conformal transformations because at late times, they act within this constant eta slice as special conformal transformations would. Does everyone know what a special conformal transformation is? Or you do an inversion, you translation, reinvert, that's it. There's some dressing with time and so on. So it's kind of complicated, but at late times, as eta goes to 0, it becomes identical to special conformal transformations. It's just the fact that SO1,4 is the conformal group, is the Euclidean conformal group. So there are 3 other generators. And these ones, they're the ones that tend to give us a lot of juice, but they're not trivial in these coordinates. So we need to work a bit harder. Okay. So this was a quick reminder on geometry. And now let me tell you how we quantize the free field, and then we're going to go to inflation. In the end, inflation is just about QFT in quasi-de Sitter space, so it will be useful to gain some intuition about So let's do the free scalar in ds. For the representation theory of the de Sitter group changes sort of dramatically between odd and even dimensions. So it's very important that we're in 4 dimensions. So I don't know if Dio will talk about that, but actually de Sitter 2 is closer to de Sitter 4 than de Sitter 3 is to de Sitter 4. That's kind of peculiar. Anyway, so this is the free field. Very simple. So let's write down the action. I use conventions that civilized people use, minus, plus, plus, plus. So this is G mu nu, D mu phi, D nu phi, plus M squared phi squared. I can still have lunch with people that use other conventions. That's okay. But because of that way of writing down the metric, and because of translation invariance, we're going to go to momentum space. Remember in the beginning I showed you how we talk about Fourier modes and so on. So we're going to go to momentum space. So similar story. You should think, so the metric is A of eta is minus 1 over H eta. So you should think of this as a collection of time-dependent harmonic oscillators. Okay? And why a collection? Because every Fourier mode looks like a harmonic oscillator. So instead of writing the classical equation of motion for the field phi as a function of time and space, you go to Fourier space and you have a time-dependent wave equation for every Fourier mode. And well, I'm going to canonically normalize for a second, and then I'm going to move back to the standard phi normalization. So canonically normalized, you define some variable v like so, 1 over h eta phi. So this variable v is called the Mukhanov-Sasaki variable, also known as canonical normalization. So if you canonically normalize the field here, because there's a scale factor dependence. By the way, I can't resist. Tarek asked me, oh, why don't you produce W bosons and photons and spin 1 particles? So why don't we do that? So if I write, okay, it's a parenthesis, okay? Let's do gauge field. And you could say I'm very fancy, I do F, wedge star F and whatever. But here, let's not save ink and let's write the metric, the salt of the earth type of way of writing it. You'd write something like this. And you can write a mass term if that is your thing, but let's just do a massless end of parentheses. So, why isn't there particle production in this model? It's a little counting exercise that you can do by staring here. Tarek doesn't count to answer the question. So, yes. So, root G has 1 over h eta to the 4th, but G inverse has h eta squared twice. So it doesn't even know that it's in curved space, okay? So that's a big puzzle, how you produce primordial photons if it's not entirely clear that they're necessary. And the usual proposals okay. So how would you fix this problem? Do you have any idea? Let's see if you discover the way people solve this problem. And you integrate them out, you mean? Yeah, that's in the right direction, but it's gonna produce a very small effect. You need something less elegant, more brutal to get the job done. So, no, it's also conformal invariance. So, something more brutal. You say it's too sophisticated. Like sophisticated people, just think of really. You need some crazy. So why do you have particle production? Because go back here. There's 1 over h eta to the 4th and h eta squared. So in the end, cosmology, curved space, blah blah blah, is just some forcing, some time-dependent forcing here. So here you got rid of the forcing. So what do? You write some function of time. That's it. So then you say some story, the 5th force, the coupling constant is space-time dependent and blah, blah, blah. So, okay, if you want to be fancy, you write a function of whatever field drives inflation. And you say, oh, I'm a reasonable guy, I'm just going to write phi. That doesn't work, okay? So then you say the words dilaton, string theory, and you write e to the phi. And that kind of starts working, and then you need to fiddle with the coefficient. It needs to be pretty large. Anyway, so this is maybe let me stop beating a dead body. This is the proposed solution, okay? Of course it does, of course it does. Let me not comment on that. Okay, so going back here, this was a parenthesis. Let's go back to this, is more interesting. So, what does the action look like? I'm gonna get some crazy, very angry emails if I keep talking about this. So, d3x d eta v squared minus div squared. So I just got rid of the time dependence here by this canonical normalization, but then it reappears in an interesting way in the mass term. This is just to build intuition, okay? Right. So the wave equation looks like this. The classical VK classical. Okay, so this is the classical, oops, classical. The classical wave equation, okay? So there are many things to unpack here. Yeah, let's keep it like this for now. First of all, when the time is very early times, as eta goes to minus infinity, you see this term gets sort of washed out. And then when you wash this out, then you're in safe territory, right? What is this? It's just a harmonic oscillator, our old friend. We know how to quantize. And the frequency of the harmonic oscillator is the absolute value of k squared. Remember that I gave you some notation that when I remove the arrow, when I talk about the absolute value of so this, it's natural to call energy. I mean, if I look at the classical equation, you see that as eta goes to minus infinity, this gets washed out, and then I just have a standard harmonic oscillator with frequency equals k. And then we know how to quantize. You should say Vk classical should go like e to the minus ik eta over root 2k as eta goes to minus infinity, okay? This is sort of the only reasonable choice for how you should quantize a field, a free field in de Sitter space, okay? So what is the story that we usually tell when this happens? You use the word blue shift, okay? So you say that we are tracking a fixed co-moving wave number, a fixed separation in x, but the physical distance between points is being blue shifted as I go to the past, right? Because the metric is not dx squared, it's dx squared divided by h eta squared. So as eta goes to minus infinity, these points at fixed x are getting closer and closer and closer. They have such short physical wavelength that we're doing experiments here. We don't care about the curvature of the universe, so we should just quantize as we. It's pretty reasonable, okay? But the argument about minimizing the Hamiltonian is a little bit suspect. And I will stop here, okay? I will just close my eyes and use this quantization condition. So this is called, as usual, it's named after people that did not invent it. So this is called the Bunch-Davies vacuum. And it has millions of names, actually. It's also called the Hartle-Hawking vacuum. It should also be called the Chernikov-Tagirov vacuum. They, as usual, the Soviet Union, they did it before in the 60s. But we also call it the Euclidean vacuum. Euclid was also thinking of quantizing the free field in de Sitter space. Because he's a little bit older than the others, maybe we should call it the Euclidean vacuum. So that's if you were to go into Euclidean signature or to Euclidean ADS, then regularity at large Z fixes the propagator, and the propagator that you would get from the Euclidean signature, weak rotated, would match with this sort of quantization condition, okay? So we're going to impose that this is the right way of quantizing. And this is mass agnostic. For any mass, if you go to very early times, you should impose that your mode functions behave like this. So this is very nice. And everything that we know, that we understand, follows from this quantization. At the free theory level, because you don't have a Hamiltonian to minimize, remember that the de Sitter group is the Lorentz group. So you either have boosts or rotations. These things are not positive definite, right? So there's no energy that's bounded from below to minimize. So there are other constructions of de Sitter invariant states. That's to say that you could have picked a admixture of e to the minus ik eta and e to the plus ik eta, and you would construct the Sitter invariant states. These, I don't know what the physical meaning of these things are. They're called alpha vacua. They've been known since forever, maybe the 80s, maybe even Chernikov and Tagirov knew about it. But it's very hard to make sense of them beyond free field theory. So for interaction theories, we keep using these and things keep working. So it's a working assumption. When we get, maybe in the next lecture, when we get to talk about cosmological correlators, we'll see that if you move away from this quantization condition, you tend to get well, when you do crazy things, you get spectacular phenomenological predictions, right? So that's depends on how you sell. Oh, I got this amazing phenomenology. Of course, you did something crazy. That's why you get the crazy, amazing phenomenological thing. So if you change the quantization condition, you can get a very striking observational prediction. That if I take n-point function, not the 2-point function. The 2-point function is too raw. The only thing you can dial is the separation between the points. But if I take 3 points, for example, and I use one of these other vacua, not the Bunch-Davies one, and I align the 3 points, the signal kind of explodes, becomes very big. So you should go in the sky, and you I correlate triangles like this. The signal is boring. Then I take this point and start going down. Boring, 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 boring. Woo, huge. Okay, we don't see any evidence of this. So then we tell ourselves some words of how it doesn't quite blow up, but it gets sort of softened, and you put bounds on it. But I think it's fair to say that we don't really understand how to do QFT beyond free field theory in de Sitter if you don't use this quantization condition. Okay, that's the best I have to offer for why this is the choice. It's really blue shift and the similarity to what you do in flat space. Now, going back here, there's something interesting that happens to the mass term. You see, when the mass, so in this way of writing it, it looks like the mass should not be bigger than 2 in Hubble units. But from this point of view, you can take any positive mass that you want. In fact, the representation theory of scalars in de Sitter allows for any positive mass. It even allows for negative mass, but this maybe you ask me later, okay? Some values of negative mass are allowed, but it's kind of there's like the weird family members there. They are separated. But then there's a continuum from mass equals 0. But you see, for light masses, it looks tachyonic. So what's happening is that this cosmological particle production that you have from the forcing of the de Sitter expansion becomes very efficient once the mass, it's always there, the effect, but it becomes very efficient once the mass becomes smaller than Hubble. That's when the Compton wavelength of the particle becomes bigger than the Hubble radius. Then you produce them very, very efficiently, very copiously. And when the mass goes to 0, you have this tachyonic production and the dilution of space-time, and they precisely balance each other so that you get a finite effect at arbitrarily late times. So that's why you have an interesting representation theory of massive particles in de Sitter space. Okay? When does the behavior, or the qualitative behavior of a quantum field change in ds? So if I go to very late times, so remember, at very early times, this gets washed out. But now as eta goes to 0, this term is becoming big, 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 huge. So how do I solve the equation of motion? I need to make v go to 0, right? If this is becoming, let's work a generic mass, big mass. So eta is going to 0. This thing is decaying, okay? What is this called? It's a very standard phenomenon in cosmology. What is this called? So you have some waves of matter. They are produced by the expansion of the universe. You produce them, great. They get produced at a given scale that we're going to discuss in a second. And then as you keep waiting, the signal that you produce starts decaying. What is this called? No. Oops. L. Yes, redshift. Very good. So it's just redshift. So as the time keeps going, the mode is getting redshifted away. Okay. So this equation is not very mysterious, okay? It's a Bessel equation. You can write but by the way, what is the Bessel function? Just a little pet peeve of mine. When you say, oh, it's the Bessel equation, the solution is the Bessel. So what is the Bessel function? It's the solution of this equation. So when you call Bessel function, all you really mean that you look at the solution of this equation, okay? So fine. Okay, it's just a pet peeve because, well, can you write in terms of special function? Like I wrote the differential equation, no, but can you write in terms of special functions? Yeah, sure. I just give it a name, Bessel function. So when does the behavior change? So as eta goes to minus infinity, looks like e to the I k eta. As eta goes to 0, you can plug in an ansatz, eta to a certain power, and you are all holographers, so I'm going to call it eta to the delta. And delta solves a famous equation, delta minus 3, with an important minus sign. Okay, this minus sign is because we are in ds, not in ADS. So when does the change of behavior happen? Well, the only dimension-less parameter that you can build is k eta. K eta order 1. So for every comoving wave number, there is a characteristic time that we call eta star, in which the fluctuation freezes and starts redshifting. So it looks like a standard plane wave, it's just oscillating, very boring, like a vacuum fluctuation in flat space. And then when k eta is order 1, it gets some kick from the expansion of the universe, it freezes and starts decaying, redshifting away. Okay? So what is the meaning of this? If you put back h and blah, 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 you'll see that that's when the physical wavelength, this is a fake wavelength, right, wave number, because it's wave number with respect to the coordinates, they're co-moving, they're not really physical. So when the physical wavelength that is getting redshifted by the expansion is of the order h inverse, that's when eta star satisfies this equation, okay? So there's a length scale, the de Sitter radius, and when the physical wavelength of your mode is becoming of the order of the de Sitter radius, that's when you change this behavior. Because this is the size of the horizon, we call this horizon crossing. So you will often see cosmologists talking about horizon crossing. And horizon crossing is just jargon to mean this. It's when the physical wavelength of a mode that you're keeping track of becomes comparable with the de Sitter radius. Okay. So the representation theory now is a bit peculiar because you should measure mass in Hubble units. So there's some order 1 number. The actual order 1 number, even though there you see 2, you should really solve this equation here, right? You see that when the m is very large, these deltas, they become complex. This quadratic has a solution plus or minus I times something. Okay, so there is really a sense in which the particle becomes heavy in Hubble units or light. So this is sort of, there's some critical regime, there's some window around 1 in which it looks like a critically damped harmonic oscillator. Then here you have just sort of over-damped fluctuations. And here, when you're close to 0, the redshift doesn't affect fluctuations. So your usual intuition of massive particles get redshifted away kicks in here. Anything of mass Hubble and lower looks massless, meaning that things decay like power laws. But the power law with which they decay depends on how far you are between 0 and this order 1 number. I mean, if you plug in m equals 0, you see that the solutions are delta plus minus 0 and 3 for m squared equals 0. So there's going to be a eta to the 0 term. That's to say that you have a fluctuation, and even though there's redshift, there was so much particle production that some of it survives to arbitrarily late times, okay? So these are the delta equals 0. They're what we call the frozen perturbations. These are the ones that inflation uses to explain why we're here. Because there is inflation, it expands and it redshifts everything away. But if I have a very light scalar, there's this competition between violent particle production and redshift, and something survives. Okay? So if I have a very, okay, maybe not exactly massless, but if I have very small, in Hubble units, massive scalar, then that's enough to generate fluctuations that I can then use to explain our universe. If you really want to know what is the actual solution of the wave equation that corresponds to this quantization condition, just to show you that I did my homework, I copied this. I have no idea how to derive it. In a desert island, I would have nothing to say. But this is the answer to nu plus 1 times, it's extremely uninteresting. It's a Hankel function of the first kind minus k eta, where, let's see if I defined, yes, nu squared is defined to be 9/4 minus m squared over h squared. Okay. Something more interesting, just to make the contact with this previous discussion of the harmonic oscillator. Here it's a little bit funny because in the discussion of the harmonic oscillator, you switch on and off the background. Here the background is switched forever. So how can you talk about in vacuum, out vacuum? And there's a bit of a cop-out that we use, which, well, okay, let me tell you what it is, and you tell me if it's convincing or not. So this cop-out only works for very heavy particles, okay? For m over h, much bigger than 1, then, so there we are in the regime where the solutions of that equation are complex valued, okay? Then as eta goes to 0, remember, as eta goes to infinity, minus infinity, the solutions are just e to the plus or minus ik eta, okay? So they look like standard plane waves. As eta goes to 0, you don't get that. You get that phi k of eta goes, there's a 3/2 factor here. This 3/2 is because when you square and you compute the power, then it decays away. Eta is going to 0, so this is decaying, right? It's decaying as eta cubed, which is matter. Matter, take a box, the box, make the box bigger, the power decays like the volume. So that's where this 3 comes from. But interestingly, you get this, eta to the minus im over h, C1. Here, this m is really not exactly the mass. That's why I took m over h much bigger than 1. It's not, there's some more annoying looking formula, but for a very large m, this is accurate. Plus eta to the im over h, C2. And I claim that this term here is related to particle production. Then there was a comment about Boltzmann suppression that I'm gonna... So this C2 here, if I were to choose the solution in the past to have only e to the minus ik eta, this C2 goes like e to the minus m over the de Sitter temperature. There's some de Sitter temperature, which the de Sitter temperature is h over 2 pi. Well, maybe there's a factor of 2 here because it's really the 2-point function that is Boltzmann suppressed. But okay. Let me put hash here, where hash is 1 or 2. I just don't remember. But why is this related to particle production? Because eta, which is minus 1 over ah, right? But if I were to go back to, and a is e to the ht. If I were to go back to cosmic time, so write it in terms of cosmic time instead of eta, then this term, okay, forget about it. But these guys here, what do they look like? Eta is e to the minus ht. So if I plug it in here, what do I get? I get e to the minus imt C1 plus C2. So now it looks like plane wave again, but with respect to cosmic time. And notice, interestingly enough, well, you're not surprised because we stare at this equation. As eta goes to 0, I wash out information about the wavelength. So the wavelength got redshifted away, super long. The particle is at rest. So all I care about is the rest mass. That's why m is appearing here. So the energy of the particle at very early times is its co-moving wave number, and at late times, with respect to different notion of time, it's the mass. Okay? So it's a bit funny, but that's the best I can do. If you were to quantize in a way that at late times you want to have this to be 0, then you would define what people call the out vacuum. And if you compute the number of out particles from the point of view of this in state, the Bunch-Davies state, the one where you quantize like so, then you get this 1 over e to the minus m over TdS minus 1. This is very famous. It's the Bose distribution. But the energy of every wave number is just its rest mass. And they are all at the de Sitter temperature. Okay? Any questions about this? So I mean, this formula looks kind of not cool, right? It's very ugly. But there are 2 values of mass for which this formula is nice. So we're going to collect those, because we're going to use those particular values of mass to gain intuition about what's going on. Thankfully, our universe is a little bit kind to us sometimes. So m squared equals to 2h squared. That crazy formula over there, vk of eta, blah, blah, blah. If you That was for this Mukhanov-Sasaki variable. But if I go back to the standard field phi classical, in this case, it's very nice, very simple, very beautiful. It's just given by this, h eta over root 2k, e to the minus ik eta. Okay, so this we can work with. Very simple. Well, it's very simple because you tune the mass precisely so that you don't even know that you're in curved space, okay? So this is called a conformally coupled scalar. So other than this redshift factor, this is not a coincidence. This is 1 over a times the standard plane wave of flat space. So it's essentially a plane wave, conformally coupled scalar. Now the case that is most interesting is this one. Here the classical, maybe should give different phi letter for it. This one is, this is the one that is most important for nature. So it's slightly more complicated. It has a little funny polynomial there, 1 plus ik eta. And it has this k cubed here instead of k. And so this is the massless scalar. And this is the one that's nice, because if I take eta to 0, if I go to very late times, this classical solution is decaying, right? It's going like eta. So the power is getting redshifted away. Even though it looks like a massless field in flat space, if I think of it in de Sitter space, its power is getting redshifted away as eta at late times. And eta is very fast. Huh? You think, oh, it's not so bad, it's decaying linearly. But eta is an exponential of cosmic time. So it's decaying super fast, okay? Super fast. So you don't see it. Now, this guy here, as eta goes to 0, it goes to h over root 2k cubed. So this is what survives. So as phi, as eta goes to 0. So that's the typical size of a fluctuation. Well, then if you're, I mean, this is pretty intuitive, right? It's phi is dimension 1, and the only dimensionful quantity that you have is h. Forget about k, okay? So the only thing that you could possibly get is h. So that's the typical size of a de Sitter fluctuation. It's controlled by the Hubble parameter, okay? So that's it. So that's all you need to know to then become expert in inflationary perturbation theory. So we reviewed the de Sitter metric. We reviewed how to think of the free scalar in ds. And now we are geared and ready to do some more realistic looking cosmology. We're going to do inflation. Before I go there, questions? Okay. Is it true that 1 hour has passed already? I have only half an hour? Okay.
Can I ask a question?
Yes.
Wasting your time even more. So what I learned from low masses is that particle production is increased greatly as you go to m to 0. So at some point, perhaps you can disregard my question if it's we can discuss it later. But what this is telling me is that I have fixed from the get-go lambda, so there is like an engine that keeps lambda fixed. But on the other hand, I have this engine supporting a huge number of particles. So what's telling me is that the Sitter, there is a problem of self-consistency, perhaps, at some point when I must take into account this production, and this is what you said, in the end, this stops inflation, right?
No, I wish what you were saying was the way we do it, which would be much more satisfactory. No, typically the stress tensor that you get from these particles is very small. compared to the stress tensor that derives inflation. So the way we do is we force the vacuum energy to go to 0. This is the dream of many people, like Woodard, Tsamis, Polyakov, Motola, but we don't know if the mechanism works. So there is the word level dream is, well, you know, you have this crazy particle production, maybe you pile up so many particles, they build up stress tensor, they back react, and they screen the cosmological constant and drive the background to something like flat space, okay? So that's their solution of the cosmological constant problem, or maybe less ambitiously, it's a microscopic mechanism for inflation. We don't know how to make that work. We don't even know if the idea makes sense. I mean, there are good reasons to believe that it doesn't work, and there are good reasons to believe that it could work, but we don't know, okay? Okay. Now let's talk about inflation. So, inflation, you need to have something like de Sitter space, but you need to stop it. Of course, it would be nice to have a dynamical mechanism to stop it. The way we stop it is by introducing a clock field that starts and stops inflation, okay? You can say that you dynamically did it, but you really didn't, okay? You just introduce some order parameter that does that for you. And the benchmark example, the simplest model of inflation, is something that is called single field slow roll inflation, okay? Single, I didn't want to write, but now I feel like I should single field slow roll inflation. So what you need is acceleration, and the simplest implementation of this is you introduce, so you have the field content is very minimal, you have the metric, it's a gravitational theory, and you have a scalar field that because you don't know what the scalar field is, you call it inflaton, okay? So we really have no idea what it is. You should think of it as an order parameter, maybe, and this inflaton has a potential that we also have no idea where it comes from. Lots of hours of ink has been spilled telling some story of where this comes from. We still don't know what it is. So we have some, and the action is really simple. So the action of this theory is integral root g. So this one we all know and love, called gravity. I'm going to write it like this. And there's some potential. And this potential is given to you. It's handed to you. You can tell some story where it comes from, but I don't care. I'm just going to write the potential, and if you're worried about effective field theory, how to think about it, then you're asking the right questions to which I don't have good answers. So we have some ways of arguing that if you draw some potential, it's probably fine within effective theories. But it's a little bit suspect if you try to think of this in some bigger quantum gravity framework. But not because energy densities are becoming Planckian or anything like that. It's just a question of, is this really a reliable effective field theory? So the typical figure that we draw looks something like this, like something along the lines of the potential that Tarek was drawing in his lectures. And you need to say where this field phi starts life. And again, zillions of ink have been spilled arguing about why you don't solve any fine-tuning problem because you need to fine-tune where phi is. This is actually kind of an interesting area where people are actually actively investigating whether it's really finely tuned or not. Anyway, so I'm going to assume that you start inflating. Once you start inflating, then I think almost everyone agrees that you will inflate. You need to ask the question, why do you start inflating to begin with? And so you need to put the field phi somewhere around here. Why do you do that? Because now you have big potential. If V of phi is big, then forget about the kinetic term for a second, then this just looks like GR with a cosmological constant, okay? So the solution is de Sitter space, where the de Sitter energy scale is determined by this V of phi. And then, okay, you're a high school student, you stare at this, and or you're like a 5-year-old toddler, you're like, okay, this ball is gonna roll, and that is true, that's what's gonna happen. Actually, it rolls a little bit slower because of the damping effect. So the Hubble rate, the expansion, slows down the rolling. So we call it Hubble friction, which is kind of not a great name, but anyway, we call it friction. Because if you write the Klein-Gordon equation for the scalar field, there is a term that it goes like h phi dots. So it looks like friction, okay? And it's proportional to Hubble, so we call it Hubble friction. Didn't have Gell-Mann at the time to give it a better name. So the scalar rolls very slowly because of this Hubble friction. And then inflation stops somewhere here. Okay? At some point, this field rolls too fast, and the kinetic term becomes important enough that it's not true anymore that the background solution is an accelerating cosmology. Okay? So acceleration, it's important to solve these causality puzzles of the early universe, that the universe accelerates. So it's very nice to have de Sitter, but maybe you can have some more time-dependent FRW cosmology as long as it still accelerates. The moment acceleration stops, when you're getting somewhere down the bottom here, then inflation ends. And then you need to explain what happens with this field. And here we don't really have ways of testing this at the moment. But the typical story is that this field oscillates around the bottom, and it couples to the standard model, and it pumps its energy into the standard model, heats up the universe. So now the metric is very much close to like almost flat, and then you fill the universe with radiation because this field phi pumps all of its energy into the standard model. You heat up the universe, and then the standard Big Bang goes. Okay? So this is called reheating. And then inflation ends somewhere here. So this is inflation. I'm going to write some formula so you can decide. I think there are some problem sets. I remember sending a problem set. I don't know if it reached the students. You can do this exercise for m squared phi squared. So you can do. If you start life up here, as you roll down there, because of this Hubble friction, it's not like you just come crashing down. You slowly move down, and then you can see that you can have enough inflation if the field is displaced enough away from the origin. Okay, so you can work all of these things out in all of its glorious detail. This model is ruled out by nature. Okay, so it predicts too many gravitational waves. But it's a nice benchmark example of how to do it. Okay. This would be the nicest model to explain. I mean, if nature really chose this, m squared phi squared would be very nice because, you know, potential was the simplest thing you write, m squared phi squared. That doesn't work, okay? Unfortunately. Nature is not choosing that mechanism. We thought, anyway, around 10 years ago when you were not thinking about doing physics, then there was a claim of detection of gravitational waves. And it fit this m squared phi squared model very nicely. Okay, there's all sorts of fantastic things that follow from if this is our universe. The Hubble scale during inflation is 10 to the 14 GeV. I don't know if that means anything to you. That's like 100 billion times the energy scale of the LHC. Okay, so that's pretty cool. You're very close to the Planck scale. You could imagine looking for strings in the sky, I don't know, all sorts of crazy things. And unfortunately, they did see a signal, but the signal was not primordial, it was galactic dust. So anyway, alas. Oh, all right, so just coming back here, let me make a comment. So this is maybe something that string theorists or particle theorists do not really appreciate, that is a standard law in cosmology, is that phi is a clock. that controls local duration of inflation. Okay? So we also call this single clock inflation. So what's the idea? So there is only one classical history. The scalar field rolls down and hits here. So this is inflation. So you could imagine that if I start on some slice here, and I keep track of a bunch of points on this slice, 1, 2, 3, 4, 5. Then each one of them undergo the same history, controlled by this clock phi. So what happens is that quantum mechanics kicks in, and these histories fluctuate in different locations. So this is the average expectation value of phi. It's space independent, but in every point in space experiences, because of quantum fluctuations, slightly different histories of phi. Okay? So the clock field, the clock ticks at slightly different rates at different points. But if the clock ticks a little bit slower, it means that you remain more time inflating. So then this point here ends up, so inflation lasts a little bit longer for this guy. Okay, so point 1 is the one for which this guy here got a little kick up the hill, and then it took longer to roll all the way down. So then point 1, you end up with a little bit more inflation space around you, gets stretched a little bit more. Point 3, though, it gets kicked down a little bit faster, right? So then you stop inflation quicker, you get less stretching. So if I start with a pretty uniform energy density slice here of constant curvature, it gets bumpy. It gets bumpy. Okay, later. And this is where we come from. Okay, that's it. So you usually learn in high school, oh, we're children of stardust and blah, blah, blah. So poetic. I mean, this is the ultimate poetry, okay? So there's a little clock that just stretches the whole universe and has little quantum fluctuations here and there. Then we wanted to set the table gets a little bit wrinkled, and the wrinkles is where stuff falls in and forms galaxy structures, humans, blackboards, and so on, okay? So that's it. That's where the quantum fluctuations come from. Okay, so and why do we get conversion of some scalar rolling down a hill to curvature? Through Einstein's equations. Okay. So let's see how that works at the level of formulas. I'm not doing well with the eraser management. Okay. So this perturbation, maybe another thing, these perturbations are really the observational meat of inflation. We say the universe expands, is almost de Sitter, but we don't observe that. We observe temperature fluctuations, galaxy fluctuations. We don't observe an expanding cosmology, okay? So perturbations are the meat of inflation, okay? That's the reason why 40-something years later, people still care about it, people still think about it, because it tells us how perturbations are distributed in the sky. So this clock field phi has some fixed history, phi bar of t, that we accommodate given some potential, but very importantly, essentially has little fluctuation, delta phi. And this delta phi gets converted into curvature through Einstein's equation. Okay, Einstein equation gets converted into the curvature, what I was calling zeta. And yeah, maybe a little bit more technical, the scalar Ricci curvature of a time slice is roughly, it's minus the Laplacian of zeta. Okay, so it's really the sort of the Newtonian potential. Okay. Let me write in the last 15 minutes. Okay. Let me write the background equations of motion. There are nice reviews about the phase space of this classical system and so on, but we're going to describe the attractor solution. So once you have initial data that is somewhere here and you don't give some crazy kick to the scalar field, even if it has a little initial velocity, it very quickly settles into this low rolling attractor phase. Okay. Of course, phase space is vast, and you can do all sorts of different things. But we work under the assumption that we're tracking the attractor of this dynamical system. So this is not very complicated. It's the Einstein equation and the Klein-Gordon equation, but the background metric is going to be FRW. So there's only one degree of freedom, the scale factor. And the field phi has some time-dependent expectation value. Okay, phi bar. Let me write phi bar, yes. So what are the equations of motion? One is the Friedmann equation. Also, the other one is the Gauss law, the constraint equation. So what do they look like? The Friedmann equation, which is just some energy budget, tells me that the Hubble rates of the universe. So this is not de Sitter anymore because the scalar field is changing its energy over time. Phi bar dot squared over 2 plus V of phi. I mean, this is as intuitive as it gets. The kinetic energy plus the potential energy of the scalar field source the overall energy of the universe that drives its expansion. Okay? And Hubble is changing over time because the scalar is rolling down the hill. Phi bar dot squared over 2. So the slow roll approximation is the approximation that the kinetic term is much smaller than the potential term. Okay? So slow roll. This is not, strictly speaking, necessary, but it's very useful. Assume V is much bigger than phi dot squared over 2. Okay? And M Planck squared. I'm using some funny conventions. I'm sure you don't care, but okay, M Planck squared is given by this. There's a nice paper of Maldacena where he says, I'm defining the Planck mass that differs from the conventions of other authors, including Planck. Okay, so this is just because of the factor of 2, so it looks like a standard kinetic term here. Anyway. So how to make slow roll precise? So now the Hubble rate, which in de Sitter was constant, h was literally just some parameter, not time dependent. Now I have a scale factor, and h is defined in the usual way. Okay, so h is defined as a dot over a. Okay, so everything is time dependent, and it's approximately constant. I'm sure mathematicians are rolling on their graves now saying approximately constant, but we are physicists, we all understand what we mean. But if something a little bit more precise, epsilon, which is the dimensionless object that controls the change of the Hubble rate in one Hubble time, and this is a sorry choice of notation, I apologize. So eta has nothing to do with time, okay? It's just the rate of change of this. It's like h double dot, So this is epsilon dot over epsilon h. So you want these two parameters. This controls how slowly you change the Hubble constant over one time, and this one controls how much the velocity changes in one Hubble time. You want these things to be much smaller than 1. Okay? So these are called slow roll parameters. There are models of inflation in which eta is large. So eta being small is kind of a simplifying assumption, but not necessary. But end of inflation, I think everyone agrees on that, because this is related to accelerated expansion. End of inflation when is epsilon equals 1. So we want, in the Sitter space, epsilon is 0. We want epsilon to be much smaller than 1. And if you really want to keep track of the whole history until the end of inflation, then you stop when epsilon equals 1. So then the Sitter-like approximation becomes really, really bad. It just means that in one Hubble time, the Hubble parameter changes by order Hubble. So it doesn't make sense to set Hubble to be a constant. Right? So that's intuitively clear? Okay. All right. So this is all there is to the background solution. It's described by two functions of time, a of t, phi of t. They solve these two equations for two functions. You can draw your favorite potential, solve it, and it's all great, wonderful. And all we really need is for a of t to satisfy these slow roll conditions. So you can think of it as approximately e to the ht with some mild time dependence on this Hubble parameter. Okay. Now, how about fluctuations? And here I'll have to continue next time because I cannot, it's time to serve the best dish of the evening, of the afternoon, but then I can't. Let me just get you excited for next time, and then we do it properly next time. So phi has some phi bars, some vacuum expectation value, and some fluctuation, delta phi. And here there's something fun you can do, is you can set it to 0. You set it to 0 by a choice of foliation. Here it's essential that it's gravitational theory. So then it reappears in the metric. What is this thing called? It's one of the most important phenomena of particle physics. So you have a scalar field acquires an expectation value, and these fluctuations disappear. They reappear in another field here, the metric. What is this called? Something else? Something else? Yes. Higgs. It's the Higgs mechanism for gravity. And now all sorts of red lights should be flaring in your brain. But I learned that there's no Higgs mechanism for gravity. It doesn't make sense to talk about Higgs mechanism for gravity. So what's the catch? Why can we talk about Higgs here? So what is the usual problem with the Higgs mechanism for gravity? So for gauge fields, you have a gauge field A mu in flat space, okay? Parentheses, just to convince you that I'm not crazy. So the parentheses. So you have a gauge field, and then you have some phi that condenses, and then write phi bar plus delta phi, and this thing here becomes phi bar and some W boson, okay? Some massive gauge field. Why Why do things work out here? It's a famous equation in mathematics. 2 plus 1 equals 3, right? So there are 2 degrees of freedom in the gauge field and 1 scalar, and you get 3. For gravity, though, this fails in flat space. Because here, this, well, I don't even know how to call H. Some massive graviton has 5, and 2 plus 1 not equal to 5. But that's because E-reps of the Poincaré group of spin 2, they're massive, carry 5 degrees of freedom. Here, then the symmetry breaking comment is important. This broke all maximal symmetries. There's no Poincaré symmetry, and very important, there's no de Sitter symmetry also, because it's time dependent. So it foliated the space-time with slices of constant phi bar, okay? Phi bar 1, phi bar 2. So it's okay now to have a graviton that is massive with 3 degrees of freedom, okay? Because there's no relativity. So that's fine. But it's exactly the same mechanism of the Higgs mechanism, okay? You just, the scalar fluctuation gets eaten. So what does the metric look like now? And then I'll stop. I'm going to quantize it next time. There's a nice way of thinking about the metric that is due to Arnold, Deser, Meissner, which is the Hamiltonian way of thinking about the metric, which is you write the metric like this. You add minus dt squared plus here I didn't really do anything. The metric in 4 dimensions has 10 entries. Here I just split the 10 entries into a 3x3 symmetric matrix and 1 3-component vector and 1 scalar, okay? So there's 10 to 10. But the neat thing that those 3 gentlemen recognized is that, if I write the metric like this, N and Ni have no dynamics. There are no time derivatives of them in the action. So they are Lagrange multipliers. The physical degrees of freedom are here. So the physical degrees of freedom. And these are constraints. So what you do is you write, so in the background solution, you write n equals 1, ni equals 0, and hij is delta ij a squared of t, okay? But now for the fluctuations, you write hij equals a squared delta ij 1 plus 2 zeta plus gamma ij. So the 3 degrees of freedom of the theory are here. The scalar that we set to 0 by a choice of foliation gets eaten and appears here through the constraint. And this is the standard gravitational wave, the transverse traceless thing that we know and love, okay? But in effort W. So these are where all the 3 degrees of freedom end up. And N and Ni, we're going to see next time, end up being functions of these. They are constraints, right? So this is some Gauss law. I set up some matter at a fixed time slice, but then the Newtonian potential needs to adjust. I need to solve the Poisson equation. I need to adjust the clock and the shear of this metric to account for the presence of these of this curved slice. So we're going to quantize zeta and gamma, and at this stage you're like, what the heck does this have to do with the free field in de Sitter space? But then after a lot of massaging and some cool miracles, you're going to get the action of free fields in a quasi-de Sitter universe for these guys here. So we're going to see that in the end, all this work of gravity, gauge, blah, 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 in the end, they have the actions. They're almost identical to the action of the free field. All of our work will be to figure out in what units they look like free fields. Okay? And we're going to see that tomorrow. So I'll stop here.
Okay, do we have any questions for Guy?
The scalar factor have another solution because before that you have a scalar factor proportional to the exponential of the Helmholtz function for
yeah,
the
no,
time.
given v of phi, the scale factor is going to have some complicated solution. The whole point is that in this low row approximation, a of t being exponential is a very good approximation.
Okay.
So, but the actual a of t, we never really care somehow. We just approximated, we take some pivot time in which, because remember, all the fun for a given mode happens at horizon crossing. So I can all I really need to know is for every mode at what Hubble scale it felt as it crossed the horizon. So here what happens, as the scalar field rolls down, there's this phi and v of phi. As the scalar field rolls down, the effective Hubble rate will change over time. So for every mode that's getting stretched, it feels slightly different Hubble rates. The modes that are stretched, that exit the horizon very early during inflation, they experience large h. The ones that exit the horizon later, they experience small h. Okay, so that's pretty much all you need. You don't really need to solve this in any detail beyond that.
Yeah.
What you use sometimes is you go back and then you use these equations to figure out exactly what is the map between a given wave number and Hubble rates that the wave number experiences.
Perfect, thank you.
How constraining is what we know of the standard model particles for the potential from the reheating?
Well, the standard model, it depends on how you couple this. So usually we assume that this is some singlet under the standard model, and then if you integrate out the standard model fields, then we think that it might change the potential somewhere, somewhat like this, or okay. This is a long story. So if this phi is coupled to any field in a non-shift symmetric way, all hell breaks loose, okay? So this potential is not trustable because then you get loop corrections to the potential and so on. So the working assumption is that this field phi enjoys a very high quality shift symmetry. Then you couple everything in a shift symmetric way. You couple d mu phi, j mu to your favorite standard model current. You can heat up the universe and this potential is untouched because of the shift symmetry. If you want to break this shift symmetry, of course, no shift symmetry in nature is perfect, but it needs to be super duper ultra high quality to have inflation. And that's a problem, okay? That you would think that string theory or some UV completion would help in understanding. The other thing I did not say, if you work out in your exercise sheets, m squared phi squared, you will find that for simple models of inflation, this field phi traverses Planckian field ranges. There is no issue with, oh, we're probing the Planck scale. No, it's just that you need to trust this function over a very long range of phi's. So you need this shift symmetry to be very, very good. So it's a little bit suspect in that sense. But this is just the dumbest thing you can do to generate some de Sitter-like expansion. So I'm not sure we should attach a lot of meaning to this model being exactly how the universe operates. It's just some benchmark thing of how you should think about inflation. But yeah, for standard model, I would say that the best way to avoid this issue is to couple things through gradients, and then the potential is unaffected.
Thanks.
Okay. In the meantime, that you think of some more questions, I must say that the exercises sheet is already in the web page. Yes. Yes. Excellent. Okay. If not, we thank Guy again.
Thank you.
Anasheli, do you have the talks?
There is one missing.
Ah.
So
We reconvene here in half an hour.
not here.
Yes.